Hello, problem-solving students. This video is a quick introduction into Chapter 8, which we will be discussing the mathematics of scheduling and talking about what we call task processor problems. Quick reminder before we start is that we will be skipping Chapter 7 due to the shortening of our schedule, as will the other sections of problem solving. So you are not going to be responsible if you ever see Homework 7 or whatever that's online activity 7, all that stuff. You can just skip that. Don't worry about it. I hopefully have turned it all off, but at any rate, just thought I'd mention that. So chapter 8, we're going to be focusing on what are called task processor problems. And in this video, I wanted to discuss what does that mean, what's an example of those type of problems, and then as usual, we're going to set up the problem and then talk about, well, how do we solve it? What does it take to actually formulate a valid solution? But I'll just go ahead and read out the sample problem, and then we'll kind of talk about how we might, what we're going to need to be able to figure it out properly. So suppose that unfortunately you're in a minor car accident on the way to school, and now that we're all stuck at home, this is much less likely. But let's just assume that this makes sense. But you're okay, your car is not. Insurance has you take it to a shop where they're going to do an estimate on probably also how much it costs, but how long is it going to take them to get it done? Is it going to take them 1 hour, 3 hours, 10 hours? That's a big question that they have. And in order to do that, they've determined the tasks that need to get done in order to repair your car. Number one, they're going to need to find the parts to replace. Say, for example, your bumper was messed up and your transmission, whatever, but they needed to get all the parts first. They also needed to do some body work, so work on the outside, maybe fix the paint, fix a dent, whatever. I'm not a car repair expert, but I'm just trying to make up some tasks that would make sense. They need to fix the engine. They need to paint and do the exterior finish, and fix the transmission. So as we can see, there's a bunch of stuff that they determine which need to get done, and they also know approximately how long each one of those tasks takes to get done. Now, if they only had one person working on our car, it would be a simpler problem because we would just add up all the time, and that would be that. But usually they will have multiple different people working on the car, so that it's not going to take as long, divide and conquer. Um, so let's assume that there are going to be two automotive techs assigned to your car, but they're never going to work on the same task at the same time because they'll get in each other's way. So for example, one person could work on task A while someone else works on task B, hypothetically. But basically they're going to divide and conquer. There are also some necessary restrictions on the order in which a task can be completed, just due to the necessity of the tasks at hand. So it says that the techs can't begin any work until they have the replacement parts, and that makes sense because they are not going to be able to paint the new bumper if it's not on the car, or if they don't have it, right? They need to get the parts first, then they can do the other stuff. And also the painting and exterior finish can't be done until the bodywork has been done. So let's say that they need to fix a dent. They're not going to paint it before they fix the dent. So basically, we got to do the bodywork before we do the painting. And in general, if there are a bunch of tasks that need to get done, and you have, say you're a manager and you have a bunch of employees that need to do a bunch of work, not all the tasks can necessarily be done in any order. There is an implied precedence to the order of the tasks, and that's one of the difficult parts of these questions that you have to pay very close attention to as you're solving them. And then it says all other tasks can be done in any order. How fast can the job be completed? So now, like we have a set of tasks. Those are not, once we've determined what those are not variables. Those are fixed values. And then the problem that we're going to try to solve is how do we arrange them? Should we do this task first or this task first? And how does that arrangement affect the efficiency of our problem? And if you had not considered how to solve these problems, you might just do them in order, alphabetical order, or you might kind of guess the order that you would need to do. But that's exactly what we're going to be examining in Chapter 8. Also, Chapter 8, before I forget, is going to be a 2-week process. So I'm going to do the first part of Chapter 8 this week, the second part next week, and then that should be enough to cover those problems thoroughly enough for online. But as usual, let's get into some terms, and then we'll get into the necessary assumptions and then we'll start working on how do we actually solve the problems. So the book uses the term processors for the workers in the problem. So those two automotive techs we would refer to as the processors. And the book uses a very computer-oriented approach to this chapter. And another aside is that in the realm of computer programming, this chapter is like a very relevant, very important set of ideas because like in that problem where we had people working on our cars, how computers have processors which work on the individual tasks that we're trying to do on our computer, say recording a lecture or watching Netflix or whatever. Um, and there's a lot of efficiency algorithms that go into how do we maximize the efficiency of the processors on the computer. I'm not going to pretend to understand it very well because I don't, but I know that these algorithms are very relevant in the realm of computer science as well, which is why our book uses those terms in a very computer-oriented sense. It can seem very hard for the average person to relate to these terms, but I wanted. Sorry, my headset turned itself off. I need to. This has been happening a lot. I need to figure out how to disable that. Anyways, uh, but these task processor problems, while they can seem very computery, and if you read the examples in the book, they're about satellites and computers and stuff. But my point is, it's also applicable to managers and people that are trying have a lot of tasks to get done as well. Anyways, the processors are the workers, the tasks are just what need to get done, and the processing times are how long it's going to take. These are all things that we need to know in order to solve the problem. If we don't know any of them, we can't really work on the problem. And the processing times could be in any sort of units, and there could be any number of tasks, and any number of people or processors working on these problems. And that's why they're referred to as task processor problems because of the terminology. Also, the precedence relations that I mentioned the term precedence before, those are the restrictions to the order that we're need to do the tasks in. So in that problem, we had a few precedence relations. Those would be the fact that they couldn't do any work until they had the parts, and the fact that they couldn't paint it until they fixed the bodywork. So it's like there's a formal set of restrictions on the order you must follow. The precedence relations are things that you cannot violate in these problems, and if you do, you're not really solving the problem. You're like if I told my workers to uh, fix the painting first, it's just not a valid solution because they can't. They probably don't even have the paint yet because you haven't done A, you haven't done B. It's not. You can't violate it, and that's I'm going to come back to that later, but that's the first thing that we have to keep in mind when solving task processor problems. And some tasks are independent tasks, meaning that they have no restrictions, like they can be done at any time, where there's nothing waiting on it to happen and there's nothing that has to happen first. Like for example, say well, I can't think of an example off the top of my head, but we'll look at some later. But you can imagine how like if you have a bunch of projects or homework to do, and you're trying to figure out, well, what order should I do them in, or whatever, you could some of your projects you could do at any time. It doesn't really matter if you do it first or last. But some things, like say for example, if you're trying to study for a test, it's probably smart to do the homework first, do the quizzes, do go to class, do all that first, then study for the test. Not study for the test first, because it'll be much harder without all that other work. Anyways, and then the ultimate goal is to figure out what is an optimal finishing time. Again, optimal meaning what's the best possibility, and finishing time meaning just how long is it going to, what's the total amount of time it will take to get it done. So in the automotive repair example, we want to know how much time would it take those two workers to fix our car and do all those tasks in the best possible way. And another goal of what we're trying to do is actually build a schedule, not just find how much time it will take, but also build a schedule for those workers to tell them what to do. Because if they don't, while we can also tell our customer how long it will take for the car to be fixed, we could also tell our employees what to do so that obviously they can probably figure it out. But if you're just trying to do it randomly without thinking ahead, you can waste a lot of time not doing it in an efficient order. And what we're going to be working on in this chapter is how do we do that? How do we build an optimal schedule and solve the finishing time of the project. I'm going to wrap this video up very shortly, and we'll get into digraphs in the next video, but there are a few assumptions which we make in these problems, which I thought is worth mentioning, because some of you, when you look at these problems, you're going to think this isn't very realistic, but these assumptions are made not to make the problems less realistic, but to make them manageable, because if we don't use these assumptions, the problems become much harder than they already are, and there's a certain they're pretty difficult. Notoriously, this is one of the harder chapters that we do in problem solving. So anyways, the three assumptions are: number one, versatility. All processors can do all tasks. So this is something that might not be a realistic assumption in a real problem, but it's necessary to do what we call the priority list model for scheduling. But like going back to the automotive tech example, it might not be realistic that all your employees can, say for example, fix a transmission, right? In these tests, I'm not an expert on car repair, but I can imagine in some employees are more skilled than other employees, and not all of them have the same level of competency. So it might make more sense to have employee 1 fix the transmission while employee 2 does the painting. But in this case, we're going to assume that all of them can do it. They're all going to be capable, as well as capability. They are also going to do it in the same amount of time. Uniformity assumption is that they're all going to complete them in the same processing times. And then, in the same light, say for example, employee 1, employee 2, they can both fix a transmission. One is better at it than the other. So one person, it might take 3 hours, the other it might take 7. But we're going to assume it's going to take them the same amount of time regardless. And you can always use, like, if you're applying this to a real problem, you could always average it out or estimate, because again, it's often difficult to predict things perfectly, but we can still use the math to do an estimation and probably save a lot of time. But yeah, we're going to assume that they're basically the same person, which is not, really accurate. And lastly is persistence, that once we build a schedule for them, they're going to work on those tasks without interruption and just do it in the exact amount of time that we've planned for. So, like, let's say that we tell employee number 1 to do the painting and exterior finish. They're just going to do it all, as well as the assumption that they're not both going to work together on the tasks was one of the assumptions that we also made. But that they're going to work straight and finish it. And obviously that's not realistic, because nobody's going to work for 7 hours without a break or without food or whatever. But if you wanted to, you can build break time into the processing time. We're just not going to, we're not going to worry about all those little details which are realistic, to a real, in a real problem, those things are, we'd have to consider, but those would make the problem way more complicated, and that's the reason for those assumptions. That's all for this one. Next video is on digraphs. Basically, we're going to build graphs to help us understand the precedence relations.